Hi, this is Embedded Systems, Spring 2011, Group 8. My name is Michael Francis.
I'm Solomon Wube.
And I'm getting at the Jugu.
And for our project, we created a smart home control system. The smart home control system was to use a touchscreen user interface that could communicate with multiple household appliances to turn on and to turn off.
One of the main aspects of our project was to design a capacitive touch buttons that a user can operate through a glass window.
Yeah, there were three main components of our project that we had to incorporate. We had to use the Spartan board, we had to use an 8-bit microchip processor, and we also had to design a custom PCB board where we actually incorporated those capacitive touch sensors.
For this project, my part was writing the software for the custom design board. The three major aspects of programming for the custom design board involve detecting when a capacitive touch button was pressed, communicating over I2C to the Spartan board to turn on or off a smart home device, communicating over UART to an LCD device to show the user's selections. For better clarification on some of the concepts I've just used, I2C is a serial communication protocol between two devices. So is UART. UART is also another form of serial communication protocol. So in terms of the software processes, to check to see if a button was pressed, I used the CTMU module in the microprocessor. Basically, the CTMU module from the microprocessor was using a constant current source that would charge the capacitive touch button for a certain amount of time, and you could read the capacitance of that button using the analog to digital converter module on the microprocessor. Basically, you could read the analog value of the capacitance and convert it to a digital value that the microprocessor could read. So, for instance, if a button was pressed, the analog to digital value would be lower than if the button was not pressed. And so what I did was I checked for the analog to digital value for each of the 4 buttons at a very fast rate, and to show that a button was pressed correctly, you could see on the LED device, on the LEDs above the buttons, the LEDs above the button, so that when you press the button it would light up for a certain amount of time, which meant that the microcontroller unit, the microprocessor, recognized that the button was pressed correctly. The overall structure of communication within the microprocessor used a message and message queue system. So basically, an example would be that, again, the button was pressed. A message would be sent over a message queue to a state machine function. And from that state machine function, a message over UART would go to the LCD device to basically update the status, of what the person pressed. So, or it could, if a button was pressed, a I2C message might be sent to the Spartan board to turn on or off one of the devices, as well as checking the status of the device. So for what worked, in terms of what I had to do for this project, when a person pressed one of the capacitive buttons, the LCD would be updated correctly based off that press. It would not, go to the wrong wording or whatever. It would work well. And when a person wanted to turn on or off one of the smart home system appliances, the person was able to use the capacitive button to turn on and off the devices correctly. And finally, if a device was added to the system, the LCD device would be updated correctly. Finally, for problems that I encountered was trying to detect a touch capacitive press through the plexiglass. The reason was because I had not taken into consideration the 60 Hz noise coming from the voltage powering the PCB board.
My individual contribution to the project was to design a custom PCB board, get the components, order the parts, and have the board ordered by the board house, and then once it comes in, solder it and put the components in it. I had to go through a few designs before I end up to the final one that I wanted, but eventually I did get a working design, and when the board came, I was able to solder it on time and get it tested. So in designing the board, basically this is what the design looks like, the schematics of the board. The schematics of the board is actually right here. So this was basically my part of this project, my major part of this project. And to demo that it actually works, as you will be able to see right now, if I touch one of these four sensors, the LED on top of them will light up. So you can see that this one lights up, that one does, this one does, and this one as well. So as long as this is powered by the train bus right here, it takes 5V in and it spits out 3.3V, with the help of this voltage regulator. And all the capacitive touch sensors they have jumpers. So in any case, in an event when one of the capacitive touch sensors do not work, we can remove this jumper and connect another sensor, an external sensor to it. Good news is the board worked as we expected it. We got all the functions that we wanted initially on the board to be working exactly the way we wanted it to work. Also, the board was very reliable and robust. Nothing failed when used repeatedly. It worked in all the environments. The capacitive touch sensors were responsive, so that gave us peace of mind. However, we also realized that our board could have been designed more in a better way. I ended up putting only one jumper in between the main source input for the current input and the board, so I had only one way to measure the power consumed by the board, and that was like the aggregate or the whole power consumed by the board. So that was a bit problematic when I had to do the power analysis. So definitely whoever is watching this, and if they are doing the board, they should really consider putting multiple jumpers in between components, so that would make it much easier for them to do the power analysis later on. Another thing I would have also wanted to do on the board was, instead of using just a jumper to control to measure the power being consumed by the board and basically just do a static power analysis, I would have loved to put a resistor and basically measure the voltage across the resistor through an instrumentation op-amp, and basically pass that as an input to one of the input pins on the microchip. That would have allowed the microchip processor to control its own, to monitor the power dynamically, and basically, to turn off and on peripherals if it's required to reduce the power consumed or increase, or is able to operate in a higher power consumption rate. So other than that, the board worked fine. Everything was successful. We were really happy with it, and it worked great.
My role in this project is to manage communication between system components using the Spartan board, and program a PIC board that interfaces smart home devices. Next. Spartan board is a master on the I2C communication, which actually makes it convenient for us to pool each slave devices and exchange messages between these two slave devices. So the Spartan board pools the interfacing board with the smart home devices and the sensor board, and exchange messages between these two. It also filters empty messages if this slave devices doesn't have any valid message to send. The Spartan board will filter these messages. The pooling happens in turns. If a message is being sent from one slave, it will be sent out to another slave, and the pooling will be held till this message will go across the bus. Regarding the interfacing board to a smart home network, which is called the Insteon network, I used a PIC board. I programmed that PIC board to interface our system to the smart home network, which is an Insteon home network. So it actually decodes and encodes a message from a smart home to our system messaging standard, and from our messaging standard back to the Insteon messaging standard. This happens to send out a message or to send out a command to those Insteon devices, for example, to turn on a device, to turn off a device, to link a device to the linking network, and similar commands. I was able to send messages between slave devices and filter out empty messages. That worked really well. In addition, the Insteon network interfacing PIC was fairly good. We only supported 13 commands. We could have supported more than that, but for the given time, we only supported 13 commands. In addition, we only support up to 5 devices to be added on the Insteon network that our PIC can manage. That could have been an improvement too, supporting more devices. What didn't work well was on the Spartan board. We had few issues about some of the slaves holding the clock while the I2C communication, but that was mentioned to be solved by using the watchdog timer. So we can add that one to our system to reset the whole system whenever there's not responding slave on the bus.
To the next device.
Oh, okay.
And turn on that device.
Yeah. All right. Count all these out. It's interesting, isn't it? Send an email out.
Finally,
Make sure
I
you
will
got
be
everything before you make an appointment.
turning on this device.
I should just make it incomplete, just on the basis that nobody.
So turn them off now, all of them?
Nobody is ready.
And now I will turn them off, but not consecutively. I will turn them off in different O's. So I'll turn off light 2 first.
You got lucky.
As you can see on the screen, the stats will be turned on. And then I'll turn on that
Yeah,
light.
they're $2 a piece, and I told you to announce what's your penalty if you didn't bring this entire kit back.
Finally, I'll turn on
Pristine
that light.
condition.
I was just gonna go myself.
And
Incomplete for the court.
again, once you turn it off, the new status light will be that it's turned off.
So it's incomplete for the court. So, it's funny how, no. I'll just put it off the